Hello, and a very warm welcome to everyone. Have you ever looked at an electrical diagram and seen those squiggly lines, the sine waves, and felt a little intimidated? They represent the alternating current, or AC, that powers our homes and cities. Analyzing circuits with these constantly changing waves can involve some pretty heavy-duty math, like calculus. But what if I told you there was a mathematical magic trick? A way to take those dynamic, wiggling waves and transform them into simple, static arrows? A technique that lets us ditch the calculus and solve complex AC problems with the straightforward algebra you learned in high school? Well, that trick exists, and it's called a phasor. Today, we're going to demystify this incredible tool. By the end of this video, you'll understand what a phasor is, why it's so useful, and how to represent it mathematically. Let's get started. Our topic is the mathematical representation of phasors. There are three main ways we can write them down: rectangular form, polar form, and exponential form. They are all just different languages to describe the exact same thing, and today we're going to master the foundational one, the rectangular form. But before we can understand the representation, we need to deeply understand the thing it's representing. And it all starts with this equation: V of t equals Vm sine of omega t plus phi. This is the heartbeat of AC electricity. It describes a sinusoidal voltage or current as it changes over time. Let's break it down, piece by piece, because every single symbol here tells an important part of the story. First, we have V of t. The V stands for voltage. The little t in the parentheses is crucial. It means as a function of time. This isn't like a battery, which provides a constant DC voltage. This voltage is alive, it's dynamic. It's continuously oscillating, going from positive to negative and back again in a smooth, wave-like pattern. Think of it as the pressure in a water pipe that is constantly pulsing. Next, we have Vm. This is the amplitude. The M stands for maximum. So, Vm is the peak value, the highest point the voltage wave reaches in its cycle. If you imagine a wave on the ocean, the amplitude is the height of the wave from the calm sea level to its crest. When we say the power from a wall outlet in North America is 120 volts, that's actually a related value called the RMS voltage. The peak voltage, RVM, is actually higher, it's about 170 volts. So Vm tells us the strength or intensity of the wave. The sin tells us the shape of the wave. It's a sine wave, which is a very specific, smooth, and repetitive pattern of oscillation. Nature loves this shape. It describes everything from light waves to the motion of a pendulum. We could also use a cosine wave, which is the exact same shape, just shifted in time. We lump them both together and call them sinusoids. Now for the part in the parentheses, omega t plus phi. This entire expression is called the argument of the sine function. It's the engine that drives the wave forward. The first part is omega t. The Greek letter omega represents the angular frequency. This tells us how fast the wave is oscillating. Think of a spinning bicycle wheel. Angular frequency measures how many radians, or how much of a circle, the wheel turns through every second. A higher omega means a faster spin and a more rapid oscillation. It's directly related to the frequency F you might be more familiar with, which is measured in hertz. For the 60 Hz power in our homes, the angular frequency is about 377 radians per second. As time t marches forward, the term omega t continuously increases, driving the wave through its cycles. And finally, we have the Greek letter phi. This is the phase angle or phase shift. This is a concept that sounds complex but is actually very intuitive. The phase angle tells us the starting position of the wave at time zero. Think of it like a race. If two runners start at the exact same time from the starting line, they are in phase, and their phase difference is zero. But if one runner gets a head start and is already a few feet down the track when the starting gun fires, they have a positive phase angle. Phi tells us how much of a head start or a delay our wave has at the very beginning of our measurement. Okay, so that's our complete, time-varying sinusoid. It's a beautiful description, but it's a bit of a handful to work with. This is where the phasor makes its grand entrance. Let's focus on the definition. A phasor is a complex number that represents the amplitude, Vm, and the phase, phi, of a sinusoid. Notice what's been left out. The entire time varying part, the omega t. How can we just ignore that? Well, in most AC circuits we analyze, every single voltage and current is oscillating at the exact same frequency, omega. Since it's common to everything, it doesn't give us any unique information about the relationships between the waves. So, for the sake of simplicity, we agree to set it aside. A phasor is like taking a photograph of our wave at a single instant in time, specifically at time equals 0. This snapshot freezes the wave, capturing the only two pieces of information that distinguish it from other waves in the circuit: its maximum height, Vm, and its starting position, phi. You can visualize this as an arrow, or vector, anchored at the origin. Imagine this arrow is spinning counterclockwise at a speed of omega. The length of this spinning arrow is our amplitude, Vm. The angle it makes with the horizontal axis at any moment is our full argument, omega t plus phi. A phasor is what we get when we hit the pause button at the very beginning, at time t equals 0. The arrow freezes. Its length is still Vm, and its angle is now just phi. This frozen arrow is our phasor. It's a static object that has a magnitude, its length, and a direction, its angle. And now, the question becomes, how do we describe this arrow mathematically? That brings us to our first method, the rectangular form, also called the Cartesian form. It describes the location of the tip of our phasor arrow using simple horizontal and vertical coordinates, just like plotting a point on a graph. The formula is z equals x plus jy. Let's give this a detailed treatment. Z is simply the standard name we give to a complex number in this context. Z is our phasor. X is the real part of the complex number. This is the horizontal projection of our phasor. Imagine a light shining straight down from above. X is the shadow the arrow would cast on the horizontal axis. Using basic right triangle trigonometry, we can see that this horizontal side x is equal to the hypotenuse, Vm, times the cosine of the angle, phi. Y is the imaginary part of the complex number. Similarly, y is the vertical projection. Imagine a light shining from the right. Y is the shadow the arrow would cast on the vertical axis. From the same triangle, the vertical side y is equal to the hypotenuse, Vm, times the sine of the angle, phi. And now for the mysterious j. This is the imaginary unit. Don't let the name imaginary fool you, its effect is very real. In mathematics, j is defined as the square root of -1. But in this context, it's easier to think of j as a directional marker. Its job is to tag the y value and tell us, hey, this part of the number is not on the horizontal number line. This part is on the vertical axis. It's what allows us to combine two independent pieces of information, a horizontal value and a vertical value, into a single number. You've probably seen this as I in math class. So why j? It's a purely practical choice made by engineers. In electrical engineering, the letter I is almost universally used to represent electric current. Using I for both the imaginary unit and for current in the same equation would be a recipe for disaster. So, engineers adopted j to keep things clear. It means the exact same thing. So, when we write our phasor in rectangular form as z equals x plus jy, we're essentially giving a set of directions. To find the tip of the phasor, start at the origin, move x units along the horizontal real axis, and then move y units along the vertical imaginary axis. So let's tie it all together. We begin with a real-world, time-varying signal like a voltage wave. To simplify our analysis, we transform it into a phasor. A phasor is a snapshot that captures the wave's two key characteristics, its amplitude and its phase. The rectangular form, z equals x plus jy, is one way to write this phasor down. It describes the phasor in terms of its horizontal, real, and vertical, imaginary, components. And while we focused on this form today, the other two forms are just as important. The polar form is even more direct, writing it as Vm at an angle of phi. And the exponential form, Vm times e to the power of j phi, is a compact and incredibly powerful form used in more advanced calculations. The true power comes from being able to effortlessly convert between these forms, choosing the best one for the job at hand. Mastering this simple concept of the phasor is the single most important step in moving from basic DC circuit analysis to understanding the fascinating world of AC circuits. Thank you so much for joining me today. I hope this detailed explanation has made this topic crystal clear.